Hello everyone, I'm Yushibin Ilyas from University of Applied Sciences Osnabrück. The topic of this presentation is virtual sensor creation to replace faulty sensors using automated machine learning techniques. And this research is funded by the research project IoT Crawler, which is part of the European Union's research program Horizon 2020. This presentation is divided into the shown sections. I will start off with the introduction and motivation behind the concept of virtual sensors. Why do we need them and why do we need an automated solution? The next section illustrates what steps should be taken to create virtual sensors through an automated approach. I will then proceed to elaborate how such a framework can be designed and what are the prerequisites for creating such a framework. In the last two sections, I will show you some results and discuss the advantages as well as limitations of virtual sensors. We all know the impact IoT sensors have on the world. Billions of IoT sensors are deployed all around the world, empowering smart cities, smart industries, smart homes, etc., with the purpose of conveying some sort of information about the environment to the concerned people, or to automate certain processes in the form of machine-to-machine communication. With such a huge number of sensors with different types, different attributes, there is a need for platforms which can crawl and search these sensors to provide users with as accurate information as possible. The attributes to have the search can be the type of the sensor, its deployed location, unit of measurement, and even precision, among others. One huge problem that can occur is different kinds of faults which make a sensor useless. These faults can occur because of hardware failures like broken sensors, dead batteries, etc., or they can also occur due to network failures, due to which the required data cannot be published to a central repository. To cope with the situation, we propose here the idea of using virtual sensors in place of the faulty ones. The virtual sensors are soft sensors or estimators created through machine learning techniques by utilizing the historical data of the faulty sensors along with the historical data of the sensors with similar specifications. However, even this does not solve our problems as there is no analyst or human in the loop, because when we have a search platform that deals with such a large number of IoT devices, it is not really possible to have someone look at the problem every time there is a fault in some sensor. So usually to solve some machine learning problem, we look at the data, see what kind of problems the data have to clean it, decide to use some algorithms based on our analysis of the data and the problem that needs to be solved. And then based on the results, we decide if we can improve the results through fine-tuning our algorithm, or do we need to use another algorithm, or have we achieved the best results we could. However, in this scenario, as there is no human in the loop, it means we cannot go through these steps. We cannot know about what kinds of cleaning techniques are needed, what kind of data do we have, what patterns exist in this particular data, and consequently, we cannot determine which algorithm would serve us best for the given data of some failed sensor. This is the reason why we have used automated machine learning. There are different ways to use automated machine learning for a problem. The approaches we have experimented with in this research are grid searching and ensemble learning. This figure will provide you with an overview of the framework. We start with detection of a faulty sensor, and after we get a faulty sensor, the search platform will look for the adjacent sensors. By adjacent sensors, I mean sensors that are in the same geolocation or sensors that are placed inside the same infrastructure. The framework will then proceed by acquiring the sensor data of these adjacent sensors. But before we feed this data to the learning algorithms, we need to go through two important steps here. The first step is pre-processing of data, where we will clean our data and make it usable for the algorithms. Keep in mind that all of this is automated, so we cannot apply different cleaning procedures for different data sets that have different kinds of problems in them. The cleaning process is universal here and will treat all the data in the same way. After we have finished with the pre-processing, we will find the correlations of the adjacent sensors with our faulty sensor and then use only the sensors with high correlations for the learning process. Now our data is prepared. but there is still a question about which class of algorithms do we have to apply, whether we are dealing with a classification problem or a regression problem. To find the answer, the framework will look at the number of unique values in the faulty sensor. If we have a regression problem, then there will be a lot of unique values in our data compared to a classification problem, because in classification problem, we have a very small number of classes compared to the size of the dataset. So here we need to set a threshold which will decide the class of algorithm that has to be applied. In our experiments, we have used 5% as a threshold value. So if the unique values are less than 5% of the total data, then the data will be fed to classification algorithms. Otherwise, regression algorithms will be applied. For the learning phase, we have experimented with grid search and ensemble learning. If ensemble learning is used, then the model is deployed after the training. However, if grid search is used, then the accuracy of the used algorithms will be compared after the training, and the model with the best result will be deployed. The information about how a virtual sensor is created, which algorithm performed best, what were the attributes of the faulty sensor, will all be stored as the metadata of that virtual sensor, which will enable a faster deployment of a virtual sensor if a sensor with similar attributes becomes faulty in the same environment. Metadata enrichment is one of the important requirements for this framework to perform better. I have listed here some attributes of the sensors which can help the framework in different ways if they are added in the metadata. Sensor type defines what type of sensor we are dealing with. For example, if it is a temperature sensor or humidity sensor. The next two attributes helps in the searching of adjacent sensors. Sensor location defines geolocation and altitude where the sensor is deployed, while relationship to a higher entity explains how different sensors are connected to each other. The rest of the three attributes help in the pre-processing of the data. Data type describes if the recorded values are numerical or alphanumerical, which can help the framework in determining if it needs to apply data transformation techniques. Update interval tells us the frequency with which a sensor logs its data. The last attribute tells us how a missing value is annotated in the given data. Data preprocessing is another important feature of this framework. As I explained earlier, that the preprocessing options are applied universally to all the datasets and cannot be customized for each dataset individually. It means we don't have a lot of options here to apply, but there are some things that are very crucial in every case. For example, if we have data from different sensors with different update intervals, we need to align their data according to the timestamps. As a result, we will end up with some timestamps where there is no data available for some sensors in a particular dataset. To remedy this issue, we can either delete that sample or do interpolation to fill the missing value. Null values in a dataset are another problem that has to be dealt with. For this, we need to look at the null value indication in the metadata to see how the given data annotates the missing value, as it could be different for different data, and then remove these instances from our dataset. In data transformation, the framework converts categorical features represented as strings to numerical values. The last step we perform in pre-processing is data standardization by transforming the data to have a zero mean and unit variance. This is by no way a necessary step, but in my experience, certain algorithms like neural networks and especially sport vector machines converges really slow if the data is not standardized. The model training has been performed through grid search and ensemble learning to provide a comparison between these techniques. In evaluation, both techniques had comparable results, and the decision of which technique should be used comes down to the requirements such as training time and accuracy. For grid search, we apply different algorithms through scikit-learn, which is a Python library, and also neural networks with different configurations through Keras. For ensemble learning, we used AutoScaling. There is extensive documentation available for all these libraries, which you can easily find if you want to look at the specifications. In our experiments, grid search proved to be a lot faster, even when we trained 39 different models with different algorithms and tuning options than ensemble learning for the scenarios shown in the result section. Grid search also provides more flexibility to apply algorithms and their tuning options. However, these options has to be given to the framework beforehand. Although ensemble learning took more time to converge, it was often more accurate than the best model from the grid search. This is because ensemble learning applies different algorithms on the same data to create one model which can learn different patterns and distributions within a dataset more accurately. One more differentiation between these approaches is the storage size of the models they generate. Ensemble models usually have a lot of information to store, and as a result, its models are quite large in size compared to the models of a single algorithm for the same dataset. To show the results of the framework, I will show two scenarios. One where a virtual sensor is created through sensors of same sensor type, and another where a virtual sensor is created with different sensor types to show the validity of the framework in different scenarios. On the right side of this slide, you can see the map of the city of Aarhus in Denmark. The markers are placed on 21 solar power plants situated inside the city. These plants log their power output in watts every 5 minutes. The data used here has 24,000 samples in it, which contains power output of the plant for 4 months. The data is not logged during the night time where the power plant is idle. For experimentation, we mark the sensor at Dock 1 center as a faulty sensor, which you can see on the map as a red marker. Power plants with green marker are the plants whose data has the highest correlation with the faulty sensor. Yellow and blue markers show medium and low correlation with the faulty sensor respectively. The training time for the virtual sensor in this case was limited to the time of update interval to provide the users with an estimated value as soon as the fault is detected. For grid search, 39 different models were created with different algorithms and tuning options, and the fastest algorithm was linear regression with a training time of only 50 milliseconds. On the top right corner, you can see the top three algorithms with their tuning options and their mean absolute error from five-fold cross validation. On the test set, the best algorithm had a mean absolute error of around 15,000 and an R-squared score of 0.77. The model from AutoScalan had better mean absolute error and R-squared score, which was trained within the same time. On the bottom right corner, you can see the predictions from the neural network created through grid search and the model created through AutoScalan along with the actual values represented by the yellow line. For the next scenario, we used sensor array at CityLab in Aarhus, which is situated right in front of the Dock 1 center where our faulty sensor is placed. The sensors here can measure different quantities like temperature, humidity, wind speed, and sunlight, among others. Not surprisingly, the only correlated sensor in this case was the sunlight sensor. In the table, you can see some properties of the acquired sensor data. On the top right corner, you can see results from grid search. In this experiment, AutoScalan outperforms grid search by quite a bit. In comparison to the previous scenario, we can see that the predictions are not as good, although they are still very reliable. This is also because there is only one predictor in this scenario compared to the four in the previous case. To sum up this research, we have shown here how to create virtual sensors for faulty sensors with automated approach. In large-scale IoT sensor search platforms, this is very useful for uninterrupted services. And we have shown here how these sensors can be created regardless of the sensor types and what elements are necessary to create such a framework. These virtual sensors do come with some limitations of their own. For example, if the allowed training time is very limited, the system may end up with a bad virtual sensor. Additionally, they should not be used where high accuracy is needed. And lastly, they should only be used for short-term spot where data is subjected to drifts. In these scenarios, after deploying a virtual sensor, the sensor provider should be informed immediately to replace faulty sensor with a real sensor. And thank you all for listening.